All right, today we're going to talk a little bit more about some of the properties of waves, particularly boundary behavior. What we've talked about a little bit before in class, we've mentioned diffraction and reflection and refraction, but what we haven't really talked about is why they do these things. And so this little video is just a quick introduction into refraction. There's some interesting things that light does. So I just want to show you really quickly. You know, one of the things that we're always told, we always think about is the shortest distance between 2 points is a straight line, right? We always think about that. But with light, that's not, the shortest distance between 2 points may be a straight line, but the quickest path between 2 points is not always a straight line. So what we're kind of talking about, let's pretend that over here is a lake and we've got a stick out in the water that we've thrown, and over here, somebody's standing here and they've got their retriever, Fido, that's with them. Fido loves to chase sticks. I don't know if that looks like a dog or a sheep or a whatever it is, but here we go. What we think about is whenever we throw a stick for the dog, what's the quickest way to get to it? Is the quickest way to get to it just to go in a straight line path? Well, not necessarily, because if we're standing on the beach, all right, the quickest thing to do, I mean, hopefully the dog can run faster on land than it can swim in water. So the quickest thing might be to travel over here to this entry point and then take a different path to the stick. And although that's not a straight line, that may be the fastest way to get to the stick. And interestingly enough, that is what light does. Light does the same thing. This is called Fermat's principle. He was the feller that figured all this out. And light takes the path that takes the least amount of time to reach its objective, or reach where it's going to. All right, and so where that becomes a big deal is at the boundaries of different media. All right, and that for today while I'm gone, this is what you guys are going to be talking about. It's really a pretty simple idea to think about. Let's say that you're driving along in your car, your pickup, and I'm going to draw. Let's see. Let me try to draw a little vehicle here. All right, so here's a little vehicle. All right, and let's put some little wheels on it. Maybe I don't know what color we're going to make them. You'll be able to see them. All right. All right, so here's our little vehicle. I'll lock all these things together so I can play with it and turn it. And let's say that we're driving around out here, and maybe over here we're on a parking lot or something that's paved, all right? And then across this boundary, maybe there's sand over here. And I think you guys, it's not hard to really figure out what would be happening. Let's say that our vehicle, while we're driving around and having fun, maybe we decide to drive this vehicle along this path as let me make the angle a little greater. We're going to do it like that. All right, so here we are in the car. And, oops, there we go. And so if the car's coming along here, or the pickup, or whatever we're driving, and we drive along this path, I want you to think about what happens right when we reach the boundary between the paved surface that's smooth and we can drive really fast on, and the sand, which we won't be able to go as fast in. If you think about it, when this car gets right to this point, you've got that front left wheel that hits the sand, and the other 3 wheels are on pavement. What's this automobile, this vehicle, going to do? If you think about it, that front left tire, when it hits the sand, isn't it going to slow down? And if you think about it, most likely, isn't it going to jerk this vehicle a little bit to the left? All right? And then it's going to make you take off and go in a different direction. So what would that next line look like when we draw it? I mean, hopefully this is really making sense to you. Whenever you reach that boundary and it jerked a little bit, was it going to make this vehicle turn? Of course it would. I mean, I think if y'all think about your experience driving, you know that would be the case, and then it's going to take off at a certain speed. All right, guys, essentially, that's what happens with light as it enters a transition from one medium to another. All right, it's pretty simple. When you go from a medium where you can move quickly, like through a vacuum or through air, and light enters another medium that's like glass or a lens or something else, it changes. And so there's some ways that we figure out the math with that. There's something called Snell's Law. Just write this down because I know you can't see my hands while I'm making this video, but Snell's Law is something we're going to get to, probably not today, but as you work through these modules and as you read the hints and look at any of that, this simple principle is really what we're working on. If you think of that little automobile analogy, I think that's going to help you a lot. You know, what I'm talking to you about right now is not a comprehensive explanation of Snell's Law and boundary behavior, but it's an idea, maybe an analogy that'll get you started. So I'm going to quit talking. I know you guys have a lot of work left to do today. Look at the Flexbook pages. Be sure and look at the information on the physics classroom, and then jump in those modules and get started. Help each other. And at the very least, if you don't understand what's going on, be ready to ask me some questions when I come back to class, and I'll straighten it out. And we've got a couple of days of lab activities where we're going to actually investigate this behavior through some lenses and get to play with lasers and some fun stuff like that. So I'm going to quit talking and you guys get started. Have a great day, and I will see you tomorrow.